I'm going to say this in the last minute I can. Good morning, everyone. Almost afternoon. Once again, it is a pleasure today to celebrate our graduating seniors. We have had a huge class of space physics and astronomy students this year, and I am happy to see so many of them presenting their capstone research at our science speaker series yesterday and today. If you missed yesterday's, you can still watch it on YouTube. And if you're watching this on YouTube, hello. But today we have 7 more presentations. They will have about 7 minutes each, and then we'll do one question while we transition to the next speaker for each one of them, so that we can try to fit it within an hour. So first up today is Jennifer James, who is going to be talking about new short-range tests of gravity. Thank you, Jennifer.
It's on, right? Okay, cool. Hi, everyone. Thank you for coming today. So what I've been working on since about maybe October, and then, of course, beforehand, is new short-range tests of gravity. My partner has been Janessa Sloan. Shout out to her. And then my mentor is Dr. Bailey of the physics department. And here we go. And so, new short-range test of gravity is a theoretical physics research project. And so essentially what we're doing is calculating a modification to the Newtonian potential. And so we want to create a potential equation that experimentalists around the world can use. And the inverse square law, Newton's inverse square law, we just want to make sure that you know it is still valid within the boundaries of our experiment. There haven't been any violations yet. And so many theoretical ideas of unification, these manifest in violations using the standard model extension framework. This framework allows us to make small arbitrary Lorentz symmetry violations, which is what we're after here in the long run. But in terms of experiments going on carried across the world, there's some in Washington, there's some California, and then some in China even. And so basically what they're doing is they're testing this equation here. It is the Yukawa potential. And so they are taking a small torque pendulum, you can think of it as a Cavendish, where the small mass right here is about, let's say, 10% the size of a penny. And so what this experiment does is it tests for parameters in this equation and hopes to find any violations or modifications to the Newtonian gravity. And so as far as work goes, Janessa, our lovely partner here, has been doing a lot of work in some textbooks. She's been getting familiar with tensors for momentum, Christoffel symbols, and she's been well understanding the action principle, which is the very key idea in our research here, as well as the Maxwell's equations. So we want to focus here on the SME's Lagrange density in the gravity sector, whereas if some of you don't know, this is the space-time metric, and K allows for symmetry breaking, and of course right here is the action principle involving the Lagrange density. So in terms of what I've been doing, I've been using the part of the space-time metric H, and we've derived some field equations that give us 2 equations for 2 fields. And so we want to solve these coupled equations with some general solutions. So we use some Green's functions, and here we are introducing a parameter, or laser pointer. There it is. We are introducing not just one exponential term, but another, and then A3 over R here is the regular gravitational term that we are used to. And so our new solution will take the form with not just one alpha and not just one lambda, but with 2 alphas and 2 lambdas. So we're introducing 4 parameters instead of, or four parameters with 2 length scales instead of 1 length scale. And so I wanted to go over this graph a little bit with you guys. So here, oh, Matt did it again. Okay, so lambda is our length scale. As you can see, gravity has been tested at larger length scales. Alpha here is our scalar modification, and this white area basically tells us that we still need to test here. And the yellow and green are areas that have been tested. They don't have any modifications to the Newtonian gravity. If they were retested, maybe we can find some with this new parameter that I'm introducing. But basically, the point of the new parameter is so we can extend into this region. And just an example of some work that I've done, I did find alpha 1 in terms of the length scalar. And with a lot more math, I will get a nice graph for you guys. In terms of experimentation that goes across the world, we're focusing on one that is in Zhejiang University of Science and Technology group in China. Again, it is the small torque pendulum, or mini Cavendish if you want to think of it that way. But they have no leads on violations of the Rents invariance thus far. And so, for future, and so our goal was to study new corrections to Newton's inverse square law, and that is coming about in a manuscript soon here in the summer. And just to be clear, we are finding the first exact solutions to short-range tests of gravity. I'll be graduating, and Janessa plans to pursue this as her thesis, along with other extensions to our model. But yes, thank you.
All right. Ooh, that was loud. We have time for one question. I prefer students over faculty if possible. But go ahead and switch off to the next PowerPoint while we're doing this. All right. Guess it isn't possible. Dr. Grutterson.
Hey, don't switch yet, because I have a question on the Yukawa potential. If you go back to it. Well, let me just say the question while you're working on that. And don't be afraid of it, okay? Work with me on it. So if you take the derivative of that potential, the gradient, with respect to R, and so it's because it's a central potential, you calculate the central force. It's got 3 terms. The second of which has an alpha gm1 m2 over r squared part to it, right? So as r gets really small, the r squared terms dominate. So at really short ranges, you're really talking about a modification of g, right? And then at intermediate ranges, you also bring the lambda parameter from the third term. And my question is, why would you force a link between those? In other words, enforce both short range changes and medium range changes. Why not choose a different potential?
I am actually, I haven't pondered upon that before, so I will have to think about it, but thank you. I don't know, maybe we can have a conversation between Dr. Bailey, you and I later on.
Our next speaker today is Lauren Perez, who's been working with Dr. Zanelin on the rise time and radius in core collapse supernovae.
Hello, I'm Lauren, and like Dr. Richardson said, my project is on rise time versus radius in core collapse supernova. My mentor is Dr. Zanelin. So a quick overview of what core collapse supernova are. First, the layers in the core will undergo fusion and then creating that iron-nickel core. The core will collapse, and then that will create an outward propagating shock wave. Once the shock reaches the surface and light is visible, that's what we call shock breakout. So the overall goal of the bigger project, we are trying to estimate the time of shock breakout from an incomplete light curve. And here are a few components of the light curve. At the beginning, that's where gravitational wave detection would be. And then after that is shock breakout, and then up at the plateau is where the supernova would actually be discovered. Methods for this, so we're going to take a theoretical curve from our model and compare that to some experimental data we get. In this case, it's right here, it's Kepler. And our model works for about the first month, and it's based on this paper by A.P. Nagy. And in that paper, we have a few key equations. First, we have the Lagrangian for a spherical star, luminosity, and then a density profile, which we'll go into a little bit later. So parameters, we love parameters. Knowing parameters for a progenitor star is pretty important for modeling, and in a lot of cases, we don't get those parameters right away. So we need to understand how to best estimate these when they're not available. Here are the parameters in our model. Everything highlighted in purple are universal parameters, and that applies to slowly rotating progenitors. And the first two parameters that we will be using in this project are radius and mass. Those are the two we're focusing on. So we found this image from a paper by P.J. Vallely, and I'd like to focus on the rightmost square over there, and we saw that it had a very linear relationship, and we thought that was interesting. And what that picture is showing is the rise time versus radius in the progenitor star. So what is rise time? Rise time is highlighted in purple here, and that's basically, it starts right before the luminosity rapidly increases in the light curve up until the peak luminosity. So a little bit more on radii in a light curve. R1 in the red line here is about 40 to 50 kilometers, and that's the radius of the protoneutron star, the inner part of the star. R2 in the purple line is about 100 to 1500 solar radii, so the radius of the shock wave at the surface. And then the R3 is the radius after the month of expansion, whatever that may be. Okay, so before we go into our model, we wanted to look at some values from other papers to see if they also agreed with the slope. Also to mention quickly, the slope on that image is 0.011. And so we looked at values from a paper by P.M. Garnovic, and we looked at their rise times and radii values given. And after running that through our model, we found a slope of 0.0133. So here we just see a comparison of the slope from that paper versus the original Vallely slope. Now getting into our model, so the first kind of data point you'll see on the graphs is for supernova 2011D, and that has a radii of 490 solar radius and 15 solar masses. So now for our next data point, we will adjust that radius value at 130%. And then for each run we do, we are going to adjust that mass until we can replicate that slope from the original paper. And here are a few equations explaining why we chose that 130%. As you can see, we have that r cubed factor at the end. And here are just a few runs where we didn't get the desired slope. Masses range from 19 to about 21. And finally, some results. So we found that a mass of around 19.8 solar masses gets us close to the Vallely slope. To go over the picture on the right, we have in blue our experimental slope from the other paper. That was 0.013. And then our model slope at 0.0134. And then the Vallely slope again at 0.011. So from this, looking at the picture on the left, we can conclude that our model can be in agreement with what this paper had said. Takeaways. So this is just a good way to make quick estimations on parameters for our models. And something to note, according to a paper by S.J. Smart, there haven't been many red supergiants over 17 solar masses discovered. This may be because they're far too reddened. And so if we're able to find more of these red supergiants over 17 solar masses, we can adjust our model and incorporate more into it. So overall, our next steps are to incorporate this into the estimation of the on-source window, which was that broader project I talked about in the beginning. So thank you to Dr. Zanlin and the LIGO Supernova team on campus and our collaborators.
We have time for one question. Oh, Janessa has one in back here.
Hello. Can you go to the second slide? I think it was your second slide. There's like a Lagrange. Oh, back. No. Oh. Keep going, keep going, keep going. You said you used a Lagrangian somewhere.
Yeah,
Yes.
it's the first equation right there
What?
listed.
Yeah. What is epsilon?
I do not remember.
Okay. No problem.
Okay.
Just wondering.
Yes, radioactivity. Thank you.
All right, let's go ahead and switch over. Is there time for one more quick question while Skyler sets up?
I know when we practiced yesterday, you explained it to me, but the 130% choosing. Do you remember what I'm talking about?
Yeah, basically we assumed constant density from that first equation. And then so once we assume that, we can isolate our mass and radius parameters. And once we solve for that, we get that r cubed. So that's as long as we're assuming constant density.
Thank you, Lauren. Next up, we have Skyler Kemper, and she's going to be talking to us about optimizing interferometers in space. Take it away, Skyler.
All right, cool. So my name is Skyler, and today I'm going to be talking about optimizing interferometers in space. And before I get into it, I would like to acknowledge Dr. Roberta Giusteri, Dr. Sarah Bukowski, Dr. Gudrun Warner, Dr. Michele Zanlin, and Mega Dave for their support, help, and mentorship throughout the process of my research and this project. But let's get into it. Oh, that was the wrong way. All right, so in order to talk about my research, I need to give a bit of a background on the Laser Interferometer Space Antenna, or LISA. And LISA is a space interferometer, which is following the success of ground-based interferometers like LIGO and other space interferometers like LISA Pathfinder. And the reason why we want to have an interferometer in space is because there's going to be a reduction in seismic and gravity gradient noise, which interferes with low-frequency observations. I believe that currently LIGO can only go as low as 5 hertz and not really into the realm of 0.1 millihertz to 100 millihertz, which is specifically where LISA is going to be observing. And in this area, we're going to be able to see different bodies like extreme mass ratio in spirals, black hole binaries, compact binaries, and a lot of other astrological bodies, which we'd be interested in looking into. And so, as you can see on the screen, LISA is a giant system of 3 satellites, which are connected by lasers, and they're going to be rotating around the sun, in orbit around the sun, following behind the Earth, which is honestly a really cool image to think about. All right, so here's an overview of the schematics of LISA. LISA has 3 different types of interferometers comprising it. So there are the long arm interferometers, the test mass interferometers, and the reference interferometers. And the long arm interferometers are the ones that extend between the different satellites, and the test mass interferometers are the ones that are actually on board the satellites. And they're surrounding the test masts themselves, which are shown by those little yellow squares and the purple circles. And the test masses are actually in free fall, which will be more relevant when I'm talking about it later on, and some of the issues that that presents. And then there's also the reference interferometers. I'm also going to briefly mention the configurations of LISA, and that just refers to which of the lasers the other lasers are being locked to, so that you know which how they're put together. All right, so before LISA can launch, there is LISA Pathfinder, which has already launched. And LISA Pathfinder is comprised of 2 satellites instead of the 3 satellites that LISA will be comprised of. And LISA Pathfinder is sort of meant to get this baseline for what an interferometer in space is going to be able to do and what it's going to look like, test the equipment, and then also look at some weather-based phenomena while it was up there. And when LISA Pathfinder was up there, there was one unexpected noise which presented itself, and that is TTL, or tilt-to-length coupling. And that was specifically the noise that I was doing research into. So TTL presented itself as this sort of red bulge that you can see on the graph over there, and that was a problem because we didn't expect it and we didn't know how to get rid of it. However, we were able to use this differential acceleration equation, which you can see at the bottom of the screen, where each of the coefficients C refer to each of the angles of motion of the spacecraft, and we're able to subtract the noise caused by TTL from the actual data that we're getting, which is how we get that blue curve, which is right underneath the red one. Even though we were able to subtract the noise for some of LISA Pathfinder's readings, we weren't confident that we'd be able to do that for all of LISA's, or that we would know what the coefficients were for LISA. So a lot of research started into seeing what those coefficients would be and other ways that we could reduce TTL. So what exactly is TTL? TTL is caused by a mixture of lateral and angular movements or jitters in the spacecraft. And because LISA uses several interferometers to combine readings and essentially create one giant space Michelson interferometer by combining them, misalignment is going to create a major issue. So TTL is kind of, I've shown it in this little diagram on the bottom right side of the screen in the most simple terms possible. But when there is movement to the spacecraft, and because the test mass is in free fall, that's going to present itself as movement in the test mass itself. And so if the test mass moves, then it's going to reflect the beam at an angle, and that's going to mess up the readings. And that's what's creating that noise. So for the first part of my project, I was looking at ways that we could see where TTL exists in sort of just the optical bench of the equipment, and if there could be any adjustments that were made into the actual optical systems that were on the satellites to see if that would improve TTL. So I was using a software called EFOCAD to create these simulations, and I show a sort of example of some of the areas that I was looking for on the right side of the screen. I was mostly looking at lateral and longitudinal shifts, as well as some changes to the measurement beam waist size and location, and I was also observing rotations around the photodiode center and what changes to that would look like. And so I was coding these in C++, and I was producing some of my graphs in MATLAB, just sort of looking and making estimations on the TTL based off of the changes that you would see from those to see if they would make a significant impact. And so I have over 100 graphs to show the process for going through that, so I don't really have time to go through all of those, so I'll just be presenting my results from that part of the project. But as you can see on the far right side of this table with the TTL noise estimations, they're all around 10 to the -9 for this specific situation where I'm looking at the resized beam waist. And that's in meters per square root hertz. And so that is well below the area that the noise would impact for LISA, so it's not presenting itself as a major problem. So this was pretty similar for all of the areas that I looked at where TTL wasn't going to be making a major issue of itself. All right, so for the second part of my project, I was looking at ways to develop the coefficients for the subtraction equation that I showed earlier on. And I was looking specifically at situations where galactic foreground noise was injected into the signal alongside the TTL noise. And the actual value for the coefficients for C were already put into the code, and I was trying to see if there were other methods for me to estimate those coefficients without pretending like I don't know them. And so for that part of my project, I was able to create these preliminary graphs just looking at TTL, the impact on that, the foreground noise added, and what those would look like. And I noticed that there was a lot of variations occurring between 10 to the -4 and 10 to the -3. So I adjusted the frequencies based off of that. And that's where I got this graph. This actually shows the estimations for the coefficients. And that blue line is showing the estimations with the shifted frequency range, and the red line is the non-shifted frequency range. And the actual coefficient line should look a lot more linear, so the blue line where we're doing the shift to the frequency range is actually a better estimation for all of the coefficients than what we started with. And then here's another graph. So for this graph, the red line is showing what I was showing on the previous graph with the blue line. But I'm also showing here with and without foreground. So the blue line is showing without foreground noise being put into it, and the red line is showing with foreground noise being put into it. And then the black line is showing just the coefficients themselves. So we can see that when you add the foreground noise, it does create an impact. But the estimations when we adjust the frequency are better than what we started with. All right, so to summarize, for the geometric TTL estimations, I was able to find that the estimations I got were all well below the desired noise range. And then for the second part of my experiment, I was able to see that the foreground noise does make a difference in our coefficient results, and that I was able to achieve better estimations for the coefficients when I was adjusting the frequencies. But if I were to continue this, I'd look at higher frequency data sets, and I would also look at adding error bars to my graph because I didn't have time to add any of those in. All right, so that gets to my conclusion, and thank you all for listening. If you have any questions, I'd be more than happy to answer them, or I highly recommend going and reading some of the papers by Dr. Gudrun Wanner because she has a lot on this subject.
Thank you, Skyler. We have time for one quick question while Alexis comes and gets set up.
So I highly recommend you all watch the 1980s The Thing if you have time before finals. It's a great movie.
Hey, Skyler.
Hello.
This looks like really good technical interferometer work. I'm glad you're doing it. So in LIGO and advanced LIGO, we've had the same alignment, sensing, and control problems.
Yeah.
And there, it's been a long process of sort of optimizing the sensing to be able to subtract it out. So do you feel like in LISA you have enough sensors to do the subtraction? It just hasn't been done because they hadn't considered the noise source? Or do you need to put in more sensors?
I think that I had actually talked with some of my professors that I had working with about that, and I don't know specifically what the plans are for LISA. I do know that they are looking at adding in more sensors just to see if they can detect that, because the noise presents itself as like this huge issue that no one expected really, that there's several different ways that they're looking at fixing it. So I think I've heard about that, but I don't know specifically what those would look like.
All right, thank you again, Skyler. Up next, we have Alexis Lane, who's going to talk about my favorite star, Eta Carina, and its not-so-variable helium-1.
Good afternoon. As Dr. Richardson said, I'm Alexis Lane, and I've been working with Dr. Richardson for the last 2 years to study Eta Carina. Today I will introduce you to Eta Carina, tell you about how we measured helium-1 and what we found from it. So what is Eta Carina? This is Eta Carina. So a little bit about Eta Carina. Eta Carina is a massive binary star system with 2 stars. One is 100 solar masses and one is 40. They orbit each other every 5.5 years at their closest point. This is Perez, and they orbit each other with a highly eccentric orbit of 0.9. The star has undergone two eruptions, one in 1837 and one in 1890. During this time, this is one of the brightest objects in the sky, and since then, Eta Carina has been an object of interest for astronomers of all kinds. So in my study of Eta Carina, I have been looking at the helium-1 lines, specifically these lines, 4713, 5876, and 7065 angstroms. And we can see how they progress over the course of one periastron passage here. While these are emission lines, my main focus has been on absorption, specifically P Cygni absorption, which is a blue-shifted absorption component accompanying a strong emission line. This occurs when material is being expelled toward the observer, and there's some debate on how this is formed in Eta Carina. Within this P Cygni absorption, we also notice additional instabilities, which we more specifically see in the 2014 periastron passage. So from this absorption component, we measure the depth and velocity, and we've done this for both the single and double, and we have fit it to a skewed Gaussian curve, which the equation is shown above. So what did we find from these measurements? We started by comparing the measurements of the depth and velocity across the 3 lines over 1 periastron passage. This is the 2020. We see that there's some repeatability in the periastron passage, which happens around the 0.0 phase. This is stronger in the velocity, not as strong in the depth. But when we look at the lines over the course of the last 3 periastron passage, this is 4713, we see very strong correlations at the time of periastron. In these plots specifically, we showed the double absorption component. The secondary component is shown by the open red dots, and the solid red dots are the primary. And we can see where the secondary takes over the primary when we look at the double peak we saw earlier. Looking at the line at 5876, we see a clear correlation at periastron for the last 3 periastron passages, and this is shown at 7065 as well, though it is not pictured. So what this means, it shows that Eta Carina, the repeatability shows that Eta Carina is a lot more stable than we originally believed. This indicates that there's no significant change in the wind collision region, meaning that there's no significant changes in the mass loss properties of the system, which has been up to some debate lately. The long-term variability sometimes observed in other lines might be just changes due to extinction in our line of sight. And this supports the hypothesis that the P Cygni is forming in the colliding winds. So I would like to thank Dr. Richardson, Connor Pickett, Emily Strawn, and Nora Abraham for all their support with this project. And that is all. Any questions?
You talked a little fast. It's okay. We have time for 2 questions. Apparently you also talk well and answered everything. Okay, Jennifer has 1.
Okay, so I'm not an astronomer. Can you explain P Cygni lines for me?
Oh, she got one. I think it's okay now. Yeah, I'll go back to the P Cygni. Okay, so P Cygni absorption. So these accompany strong emission lines, and so in Eta Carina itself, like we're seeing these when material is expelled toward the observer. So since it's moving towards us, it gets a little blue shifted, and so just kind of dips.
Any other questions? Andrea, why don't you go ahead and set up? Thank you, Alexis. Next up, we have Andrea Daly, who is going to talk about the long period orbit of the dust-producing Wolf-Rayet star, WR125.
Hello. So my name is Andrea Daly, and I have been working with Dr. Richardson for 2 years on this project, which is the long period orbit of the dust-producing Wolf-Rayet binary star system, WR125. So this system is comprised of a WC7 and an O9 companion star. And in around 1991, there was a huge dust creation outburst event, which was monitored and analyzed. And then there was just a period of calm. Nothing really happened. And then out of nowhere, in 2019, 2020, there was another huge dust creation outburst event, which we were not prepared for. So we all turned on our instruments, we turned to it, and we didn't get the initial part, but we got quite a bit of the build-up and the ending. So this system has a sister system, which is what we call it. It's called WR140, which is pretty similar in a lot of aspects to this system. So using that similarity, we then made the assumption that, like WR140, WR125 is also having a dust creation episode at periastron, which is when the 2 stars are the closest point. So that gives us a period for the first time of 28.1 years. which is a little different than its sister system, which has a period of about 8 years. But this is very important considering now we can move forward to try and get an orbit. So our data comes from the Gemini Observatory and the Keck Observatory, both located in Hawaii. We are very grateful for the data we got from the Poor Weather Program, among others. We also got the honor of time on SOFIA, which is the Stratospheric Observatory for Infrared Astronomy, which is a modified Boeing S747 SP with a 2.7 meter telescope built into it, which is amazing. But SOFIA didn't look at the stars themselves, she looked at the dust created in this outburst. So this is an infrared light curve of the system, so we can see these dust creation episodes build around 1991 and also again in 2019-2020 in the ML, K, H, and J bands. So this is a preliminary graph. We do have more data to fill in a lot of these regions, considering that there's a large region that there is not much data, but we are planning to actually update the data and get a better graph soon. So this is kind of what I did for a good portion of my research, is I looked at the spectrum of WR125. So I took the data given to us from Gemini and Keck and we normalized it, and from here you can see a lot of the different features. So right around 5875 there's this teeny tiny little dip. That's the O star. That is a helium-1 line. It's an absorption line from the O star. Then you can see this very wide, broad feature, which is a carbon-3, 5696 feature. And then you can also see another feature in the middle, which is a blend of 2 carbon-4 lines and a helium-1, which we did not fit. We only fit the O star and the carbon-3. So this is the carbon-3. This is us fitting that 5696 emission feature. This is due to measure the radial velocities. So the line is broadened to the terminal wind velocity, and we interpolate the data to find the wavelengths at which the emission features reach certain heights above the continuum. So you can see the different points that we used on the 2 sides of it. Then we can calculate what the central point of that emission is at each height. Then we can get the average radial velocity from the line, and then use the standard deviation from all of our measurements representing the proxy for the errors. And once we have all of this data, we can now fit an orbit to the WR star, which is this, which is what we've worked for so long to get to. So this is a preliminary orbit of WR125. This is a first draft of the orbit. Dr. Richardson likes to make the joke that in 28 years I have to come back and do it again to make the orbit better, but we will see about that. To get this orbit, though, we had to hold a few variables constant, which is on the slide. So we had to hold the period constant, which we got from that infrared light curve, the 2 buildups that we saw that time frame. And then the time of periastron had to be held constant as well, which is a fixed date by the half rise time of the minimum and the maximum of the infrared light curve. So these are some of the orbital elements that we found. And this is our next step. Our next step in our research is to analyze the dust of the system, which is an in-depth look at the SOFIA data that we had gotten. So this is a plot of just the raw SOFIA data that we have so far. And this analysis would include looking at the temperature and the wind lines, and potentially looking into the presence of polycyclic aromatic hydrocarbons, but that is a very far goal. These are just our initial hopes and goals that we're starting with to begin our analysis of the dust. And so where am I going from here? Again, it's updating that infrared light curve to fill in that gap to actually use the data that we have now. To analyze that SOFIA data, which involves reaching out to some of the other researchers that I have working with us on this project, and comparing it to other systems, because WR125 is a little different than other systems. And then from there, we want to continue actually writing the thesis and hopefully be published in the Astrophysical Journal by the end of this summer. But that is where we are right now. Thank you for listening.
Thank you, Andrea. Looks like we have one question, unless there's a student that wants to ask one. You all get priority.
think there's still time for the student. I am obviously a big supporter of Sophia. That's my daughter's name. So, but the question is that are you? Yeah. Are you gonna be among the people that actually gonna fly on Sophia soon?
Not this time. Hopefully in the future I can go on, but not this one.
So on your graph on the, I think it was the dust, it has the vertical axis. Is that Jansky's?
Yes, I believe so.
So is that the same on all the other ones?
No, I think that's just for the Sophia data.
And the graph, this graph's already up, and I was wondering about it. I wasn't going to ask, but here we go. Is this the thermal peak? And so, how hot is it?
Yes, I am actually not very well versed in the Sophia data as of yet. That is kind of our bigger goal that we're working towards, and we're also working with so many people who actually have done more data like this with other Wolf-Rayet systems. So I am currently in the process of doing more to that.
All right, thank you again, Andrea. Next up, we have Christopher Barkley, who is going to tell you about how we use spectroscopy to test the hypothesis of a precessing orbit for the WN4 star EZ Canis Majoris.
All right, thank you. And so again, my name is Christopher Barkley, and my mentor is Dr. Richardson. So thank you for being an amazing mentor throughout this research. And my research has been on using spectroscopy to test the hypothesis of the precessing orbit for the WN4 star EZCMA. So I'll first go over what is a Wolf-Rayet star. These stars are more massive and more hotter than our sun. They have temperatures ranging from 50,000 to 210,000 Kelvin. They have strong stellar winds that eject their outer layers out into the interstellar medium. They also have signs of the C&O cycle that's observed at the star's surface due to the convection in the star's core. And they can also be categorized into 3 different spectral types. They have a nitrogen-rich star, which is EZCMA, a carbon-rich, and an oxygen-rich star. So background on EZCMA, there's been basically 2 hypotheses going around based on past analyses. And the hypothesis I took is the binary hypothesis, which exhibits a 3.77 day orbital period with some eccentricity and then a fast epicidal period or processional period of 100 days. And precession is basically a change in star's orbit over time. Now, the other hypothesis focuses on the wind structures of the star, where the period, especially for EZCMA, is not repeated over a 2-week time span. The wind variability of the stars correlates to line profile variations, or LPVs. Then there's also co-rotating interacting regions, or CIRs, which is another wind variation factor. Now, CIRs are structures formed from high-speed wind streams that overtake the slower speed wind streams as the wind propagate outwards from the star. So this creates what's called a shocked wind zone, and this shocked wind zone increases the star's brightness by about 10%. So the data collected was from the Cerro Tololo Inter-American Observatory down in Chile, and the times of data collection was from November 2020 to March 2021. And there were 14-day observation runs with 1 spectrum per night, and we focused on 3 helium-2 lines at 4861, which is this big one there, 5411, which is this one right there, and then the 6560. And we also focused on a nitrogen 5 spectral line at 4944 angstroms, which is this little bump there. The nitrogen 5 line forms more closely to the star's core. So for the data analysis with the all the different spectral profiles, we measure the radial velocities and input those radial velocities into a program called Binary Star Solver. And that program spits out binary parameters and use those parameters to fit the radial velocity curves to the data collected. Now for the helium-2 lines, all three of them, they could not be fit with a radial velocity curve. So this is an example of the nitrogen 5 line. And the section 2 here is noticeably, the curve is noticeably quite different from the other three sections. And that, along with not being able to fit the helium-2 lines, kind of shows that it's pointing towards the system is not a binary system. And next, with the parameters for the nitrogen 5 line, we took the omega, which is the argument of periastron, and then plotted that versus T naught, the time of periastron. And what you see here is just a straight line fit. And the slope, which is called omega dot, comes up to be about 7.21 degrees per day, or about 27 degrees per orbit. And from that, we can calculate the processional period, which came out to be about 50 days, which is really fast. And along with the radial velocities, we also measured the kurtosis, skewness, and the equivalent widths. This is also another example of from the nitrogen 5 line from one of the sections. And for the radial velocity, kurtosis, and skewness measurements, there's about, basically these three graphs here, there's about 95 to 99% correlation between the radial velocity, skewness, and kurtosis. So this likely indicates that the line profile variations, or the profiles of the spectral lines shifting, is caused by wind variability. So in conclusion, or to wrap things up, this analysis from this research raises questions on the binary hypothesis, where the precession period is twice expected from the photometric observations, assuming an orbit. And also the fast precession rate would not allow to fit an orbit to a 2-week time span. And so for the future, hopefully another student can pick up more research on this star, but focus on the wind variability to hopefully come up with a better explanation as to what's going on. Thank you.
Thank you, Krister. All right, we have time for one question probably before Curtis is up. All right, Dr. Bailey.
Can you go back to the plot where you're fitting for the binary orbit? 4 plots. Yeah, that's it. So what was the difference? So you have, why are there 4 of these?
So we've measured basically a 2-week time span with 1 spectrum per night. So basically this section 1 is basically the first 2 weeks. Section 2 is the next 2 weeks, and so on.
Okay.
All right, Curtis, come on up. We have one last talk today and our last capstone presentation for physics and astronomy this semester. You can finish setting up. And this is going to be Curtis Eggers, who's going to talk about a journey in laser frequency stabilization.
Thank you, Dr. Richardson. Ladies, gentlemen, and scientists alike, my name is Curtis Eggers. The next 6 minutes and 50 plus or minus 10 seconds will be defined by a voyage of scientific discovery, characterized by optical coherence, monochromaticity, and unparalleled directionality. And so, if you will allow me, I would like to take you with me on a journey in laser frequency stabilization. I hope you've all brought your laser safety glasses because, by golly, the laser is on. In this section, or in this presentation, we have 3 intentionally vague sections that comprise the entirety of the presentation. They consist of the beam, the mode, and the cavity. Please allow your imaginations to envision what these could possibly mean in anticipation for their corresponding slides. The beam. In this section, I will introduce you to some of the basics of the laser that we work with in this lab, as well as of just lasers in general. This is actually a class 3B laser. That 3R is a mistake, apologies for that. That operates at a wavelength of 1,064 nanometers, or 1.064 times 10 to the minus 6 meters, or at least it's supposed to. More on that later. If you haven't already, please direct your attention to the figure on the right. My hope is that you will find this plot very familiar. This is the electromagnetic spectrum. Here you will find the familiar visible wavelengths that you interact with every day, as well as an arrow indicating the approximate position of the wavelength of our laser within the near-infrared part of the spectrum, not visible, thereby making this laser somewhat difficult to work with and most certainly hazardous, not potentially hazardous. For your reference, I have provided an image taken in the visible part of the spectrum of the tabletop laser stabilization experiment. That, where's the little clicker? Yes, that right there, that is the laser. And here is a picture of me next to the laser for scale. There are a number of violations in this picture. This was staged, of course, including things such as the lack of laser safety goggles, no gloves, and a watch, among many others, I'm sure. Do as I say, not as I do. The primary problem with a laser that operates outside the visible part of the spectrum is, of course, that the laser is not visible. To protect our precious little eyes, we wear these super cool laser safety glasses. They are transparent to visible light to allow us to see, but they filter out all of the infrared light, which is why they kind of look like sunglasses in this picture. This picture was taken in the near-infrared part of the spectrum. The key foundational piece of information you need to know about lasers is that their beams are hyperbolic in nature. What does this mean? It means that they trace out a hyperbola as they travel through space. And what does a hyperbola have? It has a local minimum. That means that as you focus a laser, it does not come to an infinitesimal point, but rather comes to a point of minimum width. This is called the waist. If you will, you can kind of imagine you've got the waist, right? The laser has the waist. That's kind of what's going on here. As I alluded to earlier, the beam might not always have an exact wavelength of 1,064 nanometers. In fact, it tends to fluctuate over time. This is a simulated example of a fluctuating waveform of a beam. Wow, look at it go. This is a simulated example of a waveform of a beam that is not fluctuating. This is what we want. The mode. Mode matching is an easy enough concept to understand conceptually. Those of you who have taken optics will recall that an optical cavity can be constructed from 2 partially transmissive mirrors. An acoustic analog for this would be sound waves bouncing perfectly back and forth between the rooms of between the walls of a room, excuse me, creating resonance as they do so. In much the same way, a system of mirrors will have a specific solution that will allow light to resonate within them. This is the mode. The objective of mode matching is to focus a laser into a cavity so its mode matches that of the cavity, hence mode matching. Like so. This is our cavity. On either end, you will find a partially transmissive mirror, forming the two ends of the optical cavity. This is another view of the mode matching technique and its requisite system of lenses to make it happen. From left to right, the incoming beam is first spread out by the initial lens. The second lens then catches that beam and configures it into a big fat column of light, if you will. This is called collimating the beam. From there, a third lens then focuses the beam back down, which brings it to the desired waist and waist location. Different configurations of this setup will result in different values for the beam waist and waist location. Now one could, with trial and error, conceivably find a solution of lenses that appropriately focus the beam to the desired waist, running, of course, the risk of damaging equipment in the process. However, you know, I'm something of a scientist myself, so we use math and create models to do this. That's just some of my code. This is the solution. Dr. Rich, is it okay if I go over a little bit? Okay, well. This is the solution. From left to right, you're seeing a simulation or a model of the beam as it goes through space. The beam begins over here on the right. The vertical dashed lines are the various lenses that do what I was talking about in the mode matching slide, bringing it to the desired waist for the blue box over there, which represents the cavity. The cavity. Once again, those of you who've taken optics will be familiar with TEM modes. These patterns emerge as resonance solutions within a system of mirrors that act as a waveguide for electromagnetic waves. See E&M2 for more details. The goal here is essentially we want to create a stable 0-0 mode within the cavity. Some key takeaways are that the light that passes through a cavity can only have a integer number of wavelengths in length through the cavity. Any variation or change in the wavelength of the light will then correspond to proportional change in the intensity of the transmitted light from the cavity. Since the cavity is constructed from mirrors on either end, some of the incoming light from the beam is reflected back. The reflected light is not consistent and does indeed correspond to the resonance within the cavity. So by monitoring the intensity of the reflected light from the cavity, we can then feed that signal back into a PID controller, take its derivative, then feed that signal back into a capacitive plate on one of the mirrors of the cavity to, in real time, stabilize the cavity for a 0-0 mode. The derivative of the signal of the intensity I was talking about is simply referred to as the error signal, and this is what it looks like. Wow. This is also coincidentally the first YouTube short I've ever uploaded to YouTube. Please hit that thumbs up, subscribe, and ring that bell so you don't miss any future notifications. Now, in case you're like me, you probably need a picture to kind of help understand this a little bit more. This is a just quick diagram we threw together that explains kind of the core pieces of what's going on there. The incoming light, and there it is, hits that photodiode. That signal of intensity is transmitted to the PID controller to take the derivative. That signal, and there's more steps that go on with this, but that signal is then sent back to the cavity to stabilize that 0-0 mode. And the result is something truly of objective beauty, a stable 0-0 mode, if you will. And there she is. Wow. The next step is then taking the signal from the 0-0 mode, watching how that changes in time, and then feeding that signal back into the laser to stabilize the entirety of the beam. Thank you.
Thank you, Curtis. In your original error bar of 6 minutes and 50 seconds, plus or minus 10, your error bar was about off by, you know, a factor of 15. But anyway, We probably have time for one question, but I do know that it's getting close to 1 o'clock and some of you have classes. So if you need to leave for class, feel free to do so. Parker, you have a question.
Awesome, thank you. Nice job, Curtis.
Thank you.
So you are using a PID controller, but you're focusing primarily on the derivative part of that. Are you actually utilizing the scaling factor, the P, or the integral factor, the I, in that controller?
I believe we're using the scaling factor, but the integral factor I believe is turned down to 0. Dr. Garrison can probably correct me on that if I'm wrong on the details of that. Sweet.
All right, well, thank you again to everyone who came today, and most importantly, thank you to all of our seniors who presented, and congratulations on your upcoming graduation, and best wishes to your future.